All right, so this is called the Clausius-Clapeyron Equation. Okay. And you do not have to memorize this equation. I will give this equation to you on the test. I will give you this version, okay? But this version is something you may see as well, but I think more likely I will give you this version. Whatever it is, I'll give you the test, the equation. You do not have to memorize it. Okay. So what does this equation tell us? Okay, remember, vapor pressure is quoted at a specific temperature, right? Okay, you raise the temperature, the vapor pressure will change for the substance. Okay, you lower the temperature, the vapor pressure for that specific substance will change. Okay, the value will change. So let's say you have a vapor pressure at T1, temperature T1. Okay, let's say we're going to change the temperature, either increase or decrease it. If we increase or decrease it to T2, we will get a new vapor pressure 2. Okay? That's, just what it is. Okay? So the idea behind this equation, if I give you 3, any of these 3, you should be able to find the 4th. Okay? So this equation helps us to do that. All right? So any of these 3 variables, okay, the other one you should be able to find utilizing this equation. So the natural log of P1 over P2 equals delta H vap, vaporization, energy required to vaporize 1 mole, divided by R times 1 over T2 minus 1 over T1. So R is going to be also given to you. It's a constant. I'll give you R. And the constant for R is 8.314 joules over mole Kelvin. Okay? 8.314 joules over a mole Kelvin. I give it to you. Okay? You do not memorize it. All right, so let's do this problem. Something like this similarly will be on the exam. Okay. So the vapor pressure of ethanol is 100 millimeters of mercury at 34.9 degrees C. What is the vapor pressure at 63.5 degrees C? The delta H vaporization, which is what you see here in the equation, is 39.3 kilojoules over a mole. Okay. So let's go over this again a little bit more carefully. Vapor pressure of ethanol is 100 millimeters of mercury, mmHg, millimeters of mercury. I'll call that vapor pressure 1. At this temperature, I'll call it T1. What is the vapor pressure at this temperature? I'll call it T2. So vapor pressure VP2 is what we need to solve for. All right, so something like this on the test. Let's go over step by step what we need to do. Okay, step 1 here is I would convert these temperatures to Kelvin. Okay, why do I want to convert them to Kelvin? Okay, look at my constant. What is my constant? K. Okay, so the first thing is I would convert all my temperature T1 and T2 to Kelvin. So let's do that here. All right, so T1 here is 34.9 degrees C. Anybody remember how to get it to Kelvin? Okay, remember from Chem 1? We have to add 273. Okay, so that I will not tell you. You just remember, add 273. Remember? Yes? Okay. To get it to Kelvin, what do you need to add? 273. So I'll do that really quickly on my calculator. 34.9 plus 273 is going to be 307.9 Kelvin. Okay, let's do that for T2 as well. T2 is 63.5 degrees C. plus 273. And I'm getting 336.5 Kelvin. Okay, are we okay with all of this? Okay, T1 and T2. Okay, very good. So if it's already in Kelvin, you don't have to convert it, but if it's degree C, we have to convert it. Okay, the next thing I would do, step 2 here, is you see this delta H VAP. Okay, you see this delta H VAP. Okay, it's in kilojoules per mole. Okay, I'm going to convert it to joules over mole. Okay, I'm going to convert it to joules over mole. All right, how will I convert it to joules over mole? Very good. Multiply it by 1,000. Okay, so I'm going to multiply this by 1,000. Okay, let's go ahead and do that. So we will multiply that by 1,000. So we're going to convert that kilojoules over mole to joules over mole. Okay. Okay, why do we want to convert that to joules over mole? Okay, why do we want to convert it to joules over mole? Because R is in what? J over mole. Okay. So to do that, we have 39.3 kilojoule over mole. You're right. You're going to multiply it by 1,000, Nicholas. Correct. Very good. So 1 kilojoule is 1,000 joules. This is 39,300 joules over mole. I think now we can go ahead and move to step 3, which is plug it into the equation. Okay, this is called the Clausius-Clapeyron Equation. Don't need to know the name, but we will plug it into the equation. All right, so the equation, one more time, is natural log of P1, vapor pressure P1 over P2, equals delta H VAP, vaporization, over R, 1 over T2 minus 1 over T1. Okay, let's plug everything into the equation here. So what's P1? All right, so just let me tell you something. You're technically, everyone listen to me, you're technically not allowed to put units inside natural log. That's just a math thing, not a chemistry thing. So you don't put units. So we will put the units at our final answer. Okay, so inside the natural log or inside the log, do we put any units? Yes or no? You're just going to put in the number. Again, that's math, not chemistry. So you can talk to them. So P1 here, if you remember, is 100 millimeters of mercury. I'll just put in the 100. Divided by P2. Okay, what is delta H vaporization? Okay, it's 39,300 joules over mole. Okay, what is R? Okay, so I'll give you R. Yeah, very good. 8.314 joules over mole Kelvin. Okay. Times, what's 1 over T2? 1 over 336.5 Kelvin. Minus 1 over T1, which is 307.5 07.9 Kelvin. Are you guys okay with how... I cannot speak today. Are you guys okay with putting this on the calculator and solving for P2? Okay, let's do that now. Okay, step 4 in our final thing here is to solve for P2. Okay, in this specific problem, we have to solve for P2. All right, everybody have a calculator? Okay, let's get our calculators out. Let's do this together. Okay. Probably because of the natural log. Okay, we want to get you guys to get that P2 out of the natural log. Okay. So if you have any issues or trouble, just speak up. Okay. Here's how I do it. Now, there's many ways to do it. I'm showing you my way. If you have another way that gets you the same answer, perfectly fine. Okay, this is just my way. You can do your way. The first thing I'm going to do is 1 over 336.5. Okay, so 1 divided by 336.5 is that. Okay, minus me. This is me. I'm going to put parentheses. Again, you do your way, whatever makes you comfortable. Minus 1, minus parentheses, 1 divided by 307.9. Okay, I'm going to close the parentheses. Okay, 1 over that minus 1 over that is equal to this mess. Okay, is everyone with me so far? Okay, times this number, 39,300. Times 39,300 equals that thing. Is everyone okay? Divided by, okay, divided by 8.314. Okay, divided by 8.314. I'm getting minus 1.3048. I'm going to put in extra digits here, just a little extra. My final answer, I'll put it to the right significant figures. I'm going to put a little extra digits. This is what I'm going to write down. Did everyone get that? If you didn't get that, maybe I'm wrong. And maybe you're right. That's what I'm saying. I need a verification. You got it? Okay, all I need is one person to check my calculator. Okay, who makes the most calculator errors here? Okay, it's me. So, thank you. So, natural log 100 over P2 equals, I'm going to put a little extra digits, 1.348. I'll just do it there, okay? All right, by the way, let me just go over the units here. Okay, just want to tell you the kelvins cancel. The J over mole cancels with the J over mole. All right. All right, how will we solve for P2? Okay. This is the question. Okay, how will we solve for P2? You see that 100 over P2 is within the natural log. So we will not take the natural log, we will do the opposite. Okay, what's the opposite of natural log? Okay, the opposite of natural log is the inverse natural log. So we will take the inverse natural log of both sides. Not the natural log, but its inverse. Okay, what is the inverse natural log called? What's the inverse natural log called? We won't do natural log. We will do the inverse. What is the inverse called? Okay, it's called E. Okay, E. Okay, so here's natural log. But to get rid of that natural log, we do the inverse. Okay, it's kind of like yin and yang. Okay, okay, they are kind of like opposites. Okay, to get one, we have to invert the other. So I'm going to say take the inverse natural log of both sides. of the equation. Because you see what you do on the left-hand side of the equation, you have to do on the right-hand side of the equation. So we will say take the inverse natural log of both sides. Okay, what is the inverse natural log called? What is it called? E. E. You see that on your calculator, E. This is how we extract P2 out, which is what we need to solve for. All right, so E to the power of natural log of 100 over P2 equals E to the power of minus 1.30483. All right, here's a question. Okay, do not get stumped. It's easy question for you. What is E to the power of natural log over 100 over P2? It's just 100 over P2. It is just 100 over P2. Okay, what's E to the power of minus 1.30483? Okay, let's put that in our calculator. This is how we will put it in our calculator. All right, not natural log. Okay, second natural log minus 1.30483. Close the parentheses. 0.2712. I'll put some extra digits here. 0.271219. Okay, a little extra there. The final answer will have the right number of significant digits. Okay, and now we can just solve for P2. Okay, are we good with this? Okay, everyone know cross multiplication? You know this, Tamir, right? Okay, you put the P2 here, you put the 0.27 down there, correct? Yes, this should be easy, solving for P2. P2 is equal to 100 divided by 0.271219. What is that on our calculator? I'll round it, 369. Three significant figures because in my problem everything is three significant digits. So 369. And what am I missing here? Okay, don't write 369 on the exam. What will you need to write? The units. Okay, so never millimeters of mercury. Okay, so all I'm saying is that just put units. Okay, I see a lot of students units okay, on the answer.
So you have to round all the way through, or just round at the end?
I like to round at the end.
Okay, and then
Don't report a whole bunch of numbers. Don't report this on the test.
Right.
Okay, that's a big no-no. Just because your calculator screen puts all those numbers doesn't mean you report them, okay? Because engineering and sciences, you don't report all the numbers on your screen. Okay, what if this was a big screen TV? You're going to report all those digits?
so we were working it out, like, do we have to put how many numbers do we want to work it out with?
You see here, this has three significant figures.
I get the three significant, right? That's how I execute.
Right.
Like, when we're at maybe the 1.30483, right? How many?
That's totally up to you. That's arbitrary. Yeah. I just have I don't know what the word is, a feel. I guess, Yeah. The more I put here, the better I think this final answer will be. But if you put like just, It's a good question. If you put maybe 3 decimals, or you'll still get you'll still get close to the answer. Yeah. Really up to you and these intermediary steps. All right, so this is something that I want you to do on the test, which is coming up in February, okay? February 9th or February 10th. We still have 2-3 weeks left. All right, so everyone okay with this? So this is the same pipeline, this is the same procedure I want you to do on the quiz and on the test. Okay, they will definitely be on the test. Okay, I just want to show you one thing here before I leave this problem. So 34.9 degrees C. Let me write it here. (34.9°C), ethanol has a vapor pressure of 100 millimeters of mercury. In this problem, they raised the temperature. Okay, they raised the temperature to 63.5 degrees C. Okay, what is the new vapor pressure at this higher temperature? Which is our answer. So what does that tell you? Okay, if you raise the temperature, what do you think is going to happen to the vapor pressure? It's going to go up. Okay, why do you think will it go up? What happens when you raise the temperature of something? Will molecules move faster or slower? If something moves faster, what do you think is going to happen? More chance to break those intermolecular forces? Yes. Okay. The molecules will increase their speed when you increase the temperature. Increasing the speed, you're going to increase or more likelihood of breaking the intermolecular forces up. So one thing I'd like for you guys to know is typically if you raise the temperature, okay, what's going to happen to the vapor pressure? It will go up. Okay? Very good. This is something I'd like for you guys to know. All right, can I move on here? So problem like this, math problem, computational problem on the test. So your test will have multiple choice and 2 or 3 computational. This will be one of the computational, where you'll need to have your calculator out. Very good. Okay, this looks pretty neat for me. Usually my stuff is very sloppy. But I made a conscious effort to try to be clean as possible and organized. So this is probably the most organized you'll ever see me. Let's talk about another couple of phase changes, maybe in the next 10 minutes or so. We have a liquid going to a solid. Okay, liquid going to a solid is called freezing. Okay, and then what's the opposite of a solid going to a liquid? Melting. Okay. A fancy word for melting is fusion. Fusion. Okay? Instead of saying melting, okay, we will say the word fusion, and just like before, we will have a delta H fusion. Okay, this is the energy required to melt 1 mole of a substance. It's the energy you put in. Energy that must be inputted to melt 1 mole of a substance. Okay, what is delta H vap? Delta H vaporization, energy to vaporize 1 mole. What is delta H fusion? Energy to melt 1 mole of a substance. Okay, energy you put in. Okay, units are just the same. Okay, kilojoules over mole or joules over mole. All right, so water. Okay, 6,000 or so, 6,001, I guess, joules over mole. Okay, which is the same as about 6 kilojoules per mole. Where do you think this 6,000 joules is doing when you melt water? What is it trying to get rid of? Okay, what is it trying to melt? Hydrogen bond. Okay, so all of this melting is used to, break up the hydrogen bonds. What do you think about diethyl ether? Okay, why do you think it's a little bit more? Okay. Usually hydrogen bonds are stronger, but this is polar. Okay, why do you think this is a little bit higher than diethyl ether, ethanol? Hydrogen bonding. Why do you think methane is so low? Fusion, the energy to melt. Dispersion, okay. So the numbers are related to the strength of the intermolecular forces. Okay, the numbers are related to the strength of the intermolecular forces. All right, let's do another phase change, everyone. Okay, a solid going to a vapor. Solid straight to a vapor. Okay, we call that sublimation. Okay. A vapor going to a solid, we call that deposition. A vapor straight going to a solid, deposition. Solid going straight to a vapor, sublimation. Okay, just like that. We have a delta H sub, or delta H sublimation. Okay, this is delta H sub, delta H fusion, delta H vaporization. Delta H sublimation is the energy to sublime 1 mole of a substance. Okay, it's an energy input. You have to put in that energy in order to go from vapor to solid. Energy to sublime. Sublimation, just remember, is a gas going to a solid. Okay, or a vapor going to a solid. Units are the same. Kilojoules over mole over joules over mole. Anybody here eat banana chips? No? You don't like banana chips? Or you go to Fresh Market? Anybody here been to Fresh Market or one of those places? So I actually went to Fresh Market Friday, I think, Friday night. And they have banana chips, and they have these okra that are okra chips. Have you heard of this? Apple chips. So basically, that's sublimation. They'll take a banana, or they'll take an apple, or they take I saw okra. They'll take okra, and what they'll do is they'll sublime it. They'll take that solid piece of okra, and then they'll put it in a chamber. It sublimes, and they get all that water, that liquid, straight to a vapor. Okay? What happens is that okra, the banana, whatever, sublimes. That sublimation process gives you banana chips, apple chips, so on and so forth. Okay, so you see this a lot in food. Okay. All right, let me show you something here, and then let me show you something here, and then I think we'll just wrap up. All right, so what is vaporization again? What is the phase change in a vaporization? Liquid to a gas. Okay, the energy to vaporize 1 mole is delta H vaporization. Okay, what is melting? What is fusion? Okay, a solid to a liquid. And what is the energy, Layla, required to do that? Not delta H vaporization, but fusion. Okay, I'm going to do something here. I'm going to add these two up. I'm going to add these two up. When I add these two up, these two phase changes up, this liquid that's on the left-hand side will cancel with this liquid that's on the right-hand side. And I am left with the net equation of a solid going to a gas. But what's a solid going into a gas called? H sub, delta H sub. So what is delta H sub? You add these two, so you add their delta H's. Okay. And that's what we see here. So delta H sublimation is the delta H of fusion, which is melting, plus the delta H of vaporization, okay, which is a liquid going to a gas. Okay, we just add these two up. Okay, that's this equation here. So we have one more topic to go over, and that is the heating and cooling curve of water. This is actually something that I was told they ask a lot on the MCAT. So anybody who wants to go to that medical school or whatever, this is something you guys should know. That's page 16. Page 17 will do a problem that will be on your exam, another computational problem. So this is what we will do on Thursday. And then we will wrap up with a phase diagram on Thursday as well. So we will do another computational problem on Thursday using the heating and cooling curve of water and talk about phase diagrams. Meanwhile, on your end, start working on your Chapter 11 homework. You can watch the videos. You can do that chemistry tutor for extra credit, and work on your quiz. All right, I'll see you all on Thursday. Have a good and wonderful rest of the day.